Science Slam. Woohoo! On behalf of our executive producer, Narissa Viola, and our associate producer, Ashley Wren, welcome. I am your host, Mikhail Shapiro. I'm glad to see we're already getting into the spirit. That's perfect. That's one of our judges, by the way, so don't worry. They'll react much more nicely when you're presenting. All right, this show has three important components. First, it's our presenters. Let's give them a round of applause. Now, no matter what the judges tell you in the next hour or so, these are some of the top abstracts and top science that was submitted to this year's conference. So you guys are all wonderful, and don't let the judges tell you otherwise, okay? So the presenters are the main ingredient. Then we have the judges, and I'm going to introduce them one by one in just a little bit, and then they'll come up. But perhaps the most important ingredient of the show is you, the audience. And this is going to be different from your typical session, where you sit politely, you line up to answer questions, you look on your phones. Vladimir? No, instead, we're all going to be engaged. We're going to cheer, we're going to boo, we're going to ooh and ah, and make our presence felt, okay? That's our job as the audience. And, okay, now here are the rules. Each of our presenters is going to come up and give a 2-minute presentation. We're going to time it very precisely here on my phone, and we're going to start making noises at 2 minutes, okay, to get you to stop. Then we're going to have the judges talk for 4 minutes about you and your work and give you feedback. And then the judges are going to keep score, and they're going to, at the end, vote on their 3 favorites. But then the audience also gets to vote. Okay, so you, in your, yes, woo, exactly. So in your app, you can go to this session, and then there's an evaluation tab. And within that tab, you're going to be able to also pick number 1, number 2, and number 3. And then on top of that, during the presentations, each of the judges has been handed a special card. Maybe one of you can show what those cards look like, where during your talk or during the discussion, they can raise this card, and that means that they want you to have a drink with them, not necessarily alcoholic or whatever you want, at the gala, where they can further discuss your science with you. Okay, so that's their way of saying, I want this to mentor this person. And they can do that at any time. All right? So let me start by introducing our 4 judges, and I'm going to ask them each to come up here and take their seat. So first, Charles Caskey. Come on down. Here from Nashville, Tennessee, comes Charles Caskey. He's a professor at Vanderbilt University, an expert in all things ultrasound. Do not let his southern drawl fool you. He's from Texas, where they shoot first and ask questions later. All right. Welcome, Charles.
Testing. Thank you, Mikhail.
Our second judge is Veronica Clavillo-Jordan. Veronica is a professor at Harvard Medical School and Mass General Hospital, expert in magnetic resonance. As you can see, she is expecting. But that doesn't mean that you should be expecting anything other than tough motherly love.
I'll be nice.
Welcome, Veronica. All right. Our next judge is Kyle Newman. Kyle, come on up. Woo! Kyle is on the faculty of St. Jude's Children's Hospital. He's from Nebraska, which typically means nice, Midwestern. But if you've seen the University of Nebraska football team play, there's nothing nice about them. It's pure intensity, all right? So be ready for that. And last but not least, I want to introduce the famous, who needs no introduction, Tim Whitney. Now, Tim's a professor at King's College London, knows a lot about pet imaging, but the main thing you might notice about him is his British accent. And that's no accident, because the way you'll see him judging is the way all people with British accents judge in these kind of shows. So, welcome.
Thank you, darling. If it's not pet, I'm not interested.
All right, let's get started. Let's get our first presenter up to the stage. Juan Azcona, come on up. Yes. It's up to you. You can use that. We prefer. All right, let's.
The slides are animated.
Slides are animated, so you can
Animated.
Just click as you go along. There you go. And you can use this microphone.
Thank you.
All right, let's do it.
Ready? All right. Good afternoon, everyone. Thank you all for being here. My name is Juan Azcona, and our group is focused on imaging heart disease, the leading cause of death worldwide. And part of the reason that is because we rely on physiological markers of existing injury. We instead propose relying on early biochemical markers which precede remodeling. So we know that the heart uses long-chain fatty acids, but when there's some sort of ischemic injury such as ischemia, it then switches over to short-chain fatty acids. So we propose the short-chain fatty acid F18 labeled 2-fluoropropionic acid to image this metabolic shift by PET. And the reason we use this one is because we know it's taken up by the myocardium and it's not beta-oxidized, so it remains trapped in the tissue. We then couple this with the drug AZD3965, which is an inhibitor for the transporter of the short-chain fatty acid, because we know peripheral tissues rely on that transporter, but can freely diffuse into the heart. And we got a nice image as expected, a very high contrast image of the heart with very little uptake in peripheral tissues. Then we compare this image to that of doxorubicin-treated mice. So doxorubicin is an anthracycline therapy that causes cardiotoxicity in mice. And we observed another clear image of the heart, accompanied by an increased signal, indicative of a higher uptake of short-chain fatty acids. So we're very confident about the translatability of our approach. It's already been used for prostate cancer imaging in humans, and they observed a nice image of the myocardium in this patient. So our future studies are focused on establishing this as an incipient marker of incipient failure in different animal models, and then hopefully seeing this translated into the clinic for cardiac imaging sometime in the future. Thank you very much.
All right. Stay up there. All right, judges, let's hear it.
Can I just say, you're far too polite. Mark down one.
Loss of one. Great. Well, I'm going to mark down.
So this is ready for the clinic. I see. What's the plan there?
The plan is to we don't want just to have something that's a marker for disease. We want it to be a predictor of disease, because that's the major limiting factor to reduce disease, right?
Yeah.
Being able to diagnose it early. And so it's already been shown to be safe. It's an analog of lactate, so it just decays the lactate. The synthesis is very straightforward. It's simple. It can be automated. So these are all things that are ideal for a PET imaging agent that can be translated very quickly and effectively.
It sounds like you're going as a screening method, though, with a PET probe.
Yes, so a screening method.
Okay. All right, thank you.
Wait a minute. Boo, wait. Nice.
Yes, this was my concern.
Yes, Professor Kasky, as a judge, it should be more judgment and fewer questions, okay?
Okay, got it. Thank you.
No, I want to say that I think you were very clear and confident, so you sounded great. I think that's good. I have a question in terms of what's your team? Who do you work with? Do you have clinical partners, or perhaps already talking to some pharma, or what do you envision for later?
So as of right now, I think we still have to do a lot of work in animals to really push this forward, and we're in the process of trying to push this into several nuclear cardiologists. It's very difficult when you're dealing with FTG, and trying to replace that or even try to supplement that with this kind of imaging. But I'm really optimistic about this method. It's also used for...
Wait a minute. You're talking, giving an answer as long as the text on your slide. Come on, what's going on here? Let's keep it quick.
Yeah, I want to know why I care. I've seen a lot of tracers that go after myocardial metabolism, specifically fatty acids. What makes yours so special?
Well, it's a 3-carbon fatty acid, so it's not beta oxidized. We've actually done F18 labeling a bunch of different chains, and they end up in the myocardium in 5 minutes and wash away. This one, we've seen up to 4 hours in the myocardium.
Okay, I'm good.
We're working on something very similar, so it's excellent. One already! Come on, let's go!
All right, I think that was a great start. Let's give our first contestant a big round of applause. All right, our next contestant, please welcome Rianne Moss.
Okay, thank you. So I want you to imagine that you have end-stage heart failure, and there's only one option left, heart transplantation. However, this has one main limitation, the risk of immune rejection. So let's imagine that this is your transplanted heart. It will be recognized as non-self by our body, meaning that innate immune cells will infiltrate your heart, followed by adaptive immune cells, which will ultimately damage your tissue. Your medical doctor tells you that despite the fact that you are using immunosuppressants every single day, this will have to be monitored. The current method that they are using to monitor immune rejection is by the use of highly invasive biopsies. And it makes you anxious when you're thinking about the complications and risks that come along. So how great would it be for these patients if we could minimize the use of these biopsies? We propose the use of immuno-PET imaging to non-invasively monitor immune rejection in these patients. Therefore, in my research, we investigated the potential of immuno-PET imaging in a heart transplant mouse model, in which we have syngeneic transplanted mice, which have no graft rejection, versus allogeneic transplanted mice that have graft rejection on day 8 after transplantation. On day 7 after transplantation, we imaged the recipients using 2 immuno-PET probes, one measuring innate immune cell infiltration and the other one measuring adaptive immune cell infiltration. As you can see, using both of these immuno-PET probes, we were able to see really nice differences between rejecting and non-rejecting hearts. Also, we have preliminary data that shows that we can measure therapeutic effects as well. So in conclusion, we think that immuno-PET imaging is a really nice non-invasive way to monitor immune rejection, giving you as the organ transplant recipient fewer risks and a better quality of life. Thank you.
All right, judges, what did you like and what did you dislike in detail?
So really like the presentation, very clear, very clear. I'm a little concerned that the inflammation that you're seeing here is going to be a lot more than you might find in a normal, in an actual scenario in a human.
So what you can find in that you cannot find these effects in the clinic?
The degree that it occurs here might be a lot more in the animal model compared to the human. That's just my concern.
Yeah. No, it's a very strong animal model. We do that because if you have a more less intense model, it would of course take very long-term study. So it's a quite intense model, and thereby you have this rejection at day 8. So I totally agree that in the clinic we have to see if we can also measure these effects as well.
I really like your presentation. All your animations and figures are beautiful. So that's definitely good job with that. Yeah. I think I would have liked to see some future and over, like a forward-looking image of what you see right now. This is all in, one animal model, one mouse. So not one mouse, but so how is this really going to work in diversity?
So we actually also have data on FDG. So for now we have 3 PET probes. Of these 3 PET probes, we do think that CD8 nanobodies, which we used, are most interesting for bringing it into the clinic. And actually, this week I had really interesting conversations with ImagineIP, who have CD8 mini-bodies. So we're really interested to see in the clinic if we could apply this and we can measure therapeutic effects as well.
Yeah, I was thinking this whole time, maybe the Pilsner level in my blood's getting too low. This went right over me. I'm having a hard time seeing how she kind of stole my question. How you apply this really long term, deploy this in a clinical setting.
Yeah.
So that would be my major critique here, and maybe making that more clear.
So I just want to say I love Pac-Man. But I'm colorblind, so I don't like your color scheme.
Sorry, I was already worried about it.
But the data seems good.
Thank you.
All right, do we know who's our next contestant? Seems to be out of order on my... Yeah. So which one of you is this? Lorraine, yeah. Okay, let's move on to number 4. Xinhua Xie. Hey, welcome! Now it's number 3, yeah, but it's number 4. Yeah, this is number 3 for our course. Let's do it.
Okay, hello everyone. My name is Xinhua Xie from Taiwan, and and this is my topic, and we just have 2 minutes, so I just go to the main picture. The picture is about my study design, and I try to use the PTT to initiate the immune response, and then give the dendritic cell vaccine to improve the T cell immunity, and finally we use the anti-PD-L1 antibody to avoid the immune escape. And because the reason why we need to combine lots of the like dendritic cell and the antibody, because I just used the PTT at first, but although the photothermal conversion is good, we can make the tumor to the temperature to become the 55 degrees, but the tumor control only can be occur in a few days. So I use the NGS to predict the following. So I add the dendritic cell and the anti-PD-L1 therapy, and then as we can see, the result showed if I just use one single treatment group, there is no tumor can be cured. But if I use the PTT combined with DC, there is 17% remission rate, and also 70% in the PTT plus atezolizumab, which is the anti-PD-L1 antibody. But it was very impressive with the PTT plus DC plus atezolizumab. We can have the 50% remission rate, and also I did the re-challenge study and show no lung nodule. After the 40 days, I used the CT26 tumor tissue injected via the tail vein. So that's all my presentation.
All right, just in time.
Let's start with Tim this time.
It took me 2 minutes just to read your title. But, and there's a big but, you've included PTT, immunotherapy, nanostars. I love it!
Thank you.
Yeah, so I think my lab mates, who I think I saw them back here, will tell you they have to show me how to use Twitter. So I I say that to say this was very hard for me to follow. Maybe animations, something a little more interactive that I can walk through with you. Otherwise, this just, goes right over my head.
Okay.
That would be my biggest critique. Otherwise, this sounds really cool. I think this sounds really cool, but I'm not sure.
Okay, thank you.
Well, some motherly tough love here. Similar concerns. I think, yes, your response rates, that looks great, but halfway into it, I was like, wait, which disease are we looking at? Like, it's, I think you could have presented better, maybe introduced the problem. Why do I care? What is actually your solution? And go. Don't just present everything right away. Here, I don't know what to look at. So you need to guide the audience through your story. So just tell your story better.
Okay, thank you for your suggestion.
But otherwise, it looks like it works.
Thank you.
I've seen a bit of this before, so it was I was able to grab it, but I was finding myself looking around, as the others said. But I thought I think it's nice. It's great to see this work. That's a little It's not pet imaging. It's something a little different, here.
Come on, wait a minute.
It's good to see.
What's he saying?
Sit down.
Come on. You want to fight?
I want to learn more about it.
Thank you.
Oh, boo. Sit down. There is some pet there anyway. It's quite nice. You can see it on the left-hand side. Very beautiful.
Thank you, judges. Thank you.
Thank you.
All right. All right, I think our next contestant is Victoria Laney. Is that right?
So our work focuses on pancreatic cancer, a deadly malignancy with a poor survival rate. Pancreatic cancer is notoriously hard to treat, so efforts have been focused on novel therapies, such as immunotherapy, where antibodies can be given to a patient to promote tumor cell death. But immunotherapy doesn't work in all patients. So how can we determine which patients will respond to the treatment or not? We focused on an immune cell target called VISTA. When it's upregulated, it causes immunosuppression. However, when we block VISTA with antibodies, it induces an inflammatory environment which promotes immune activation and notably transiently increases stromal protein deposition. So we designed an MRI gadolinium contrast agent that specifically targets one of these stromal proteins. Uniquely, it's only expressed in cancerous tissues and associated with inflammation and not in healthy tissue. This allows us to measure the signals from MRI images before treatment, during treatment, and after treatment, and use it as a proxy for response. So we did that in an intrapancreatic mouse model. Once we had our groups, once we had our results, we were able to establish groups based off of a radiologically relevant criteria. And then from there, when looking at our images, we were able to see from our analysis of our signals from these qualitative images that non-responders had low signal during treatment and responders had higher signal during treatment. And then that relationship flipped as treatment progressed. And then we were able to confirm with histopathology what was going on a little bit better in the cellular level. And essentially what we saw with staining for cell morphology is that responders had little cancerous tissue and non-responders had heavy adenocarcinoma. Additionally, when we stained for our protein of interest, we saw heavy staining in the non-responders and less staining, but a fibrotic scar in our non-responders. So therefore, we think that we can use this as a way to determine non-responding and responding patients to VISTA. Thank you.
All right, don't beat me into this.
No,
all right.
She's mine. Stay away. She's mine.
Nope.
Hold on.
We arm wrestle for it.
You're wrestling too. Here, you're wrestling too.
Fair.
Victoria, I love it. I love this. Multiple reasons. Well, I love MRI, first of all. gadolinium agents. We work heavily on pancreatic cancer as well, and I think you did a fantastic job presenting the problem and really answering a need that is so dire. I mean, we really, really need something like this in the clinic. So, thank you. Yeah, have a non-alcoholic drink with me, or you can have my drink.
Yeah, just to be clear, I was about to arm wrestle her for that. I thought this was excellent. I'm not an MRI person, and you walked me through this clearly. The animations were very well used. I agree with the sentiment that our esteemed judge to my left provided. I don't really have any critiques. I thought this was excellent.
I'm a big fan of Biorender. One.
Shout out to Byron.
Right? Are we not all big fans of Biorender? I mean, actually, as a PI, the price is pretty high. Anyway, but big fan of Biorender, big fan of animations, and a big fan of your data. Have you considered making a pet version?
We've considered...
MRI, good one. MRI. What? What does that stand for? Brilliant job.
Yeah. I got nothing. This was lovely.
All right, that's going to be a tough act to follow, but Gina Dunkel is going to do her best.
So, what if we could actually see how tumor cells...
I love it! I'm going to nick your one!
My name is Gina Dunkel. I'm a PhD student at the Werner Siemens Imaging Center in Tübingen, but sometimes I fear I'm also a detective. And let me introduce my current case to you. Our crime suspect, metastasis, trying to take over the world. Number one cause of cancer mortality. So, that's pretty bad. What can we do to stop them? Metastases are masses hiding at different places. So our first mission is to find them. Let's imagine our body as a complex city. We have different inhabitants, and some of them are corrupted, not following the rules and causing trouble. But there are many different places to hide. So what if we could just make them visible? What if we could actually see and identify their crime suspects, helping them to support them? So here's where we start our investigation with the help of a little bit of magic called clearing. We stop time and we make the city invisible. So we find our crime suspects and we see their little helpers before it's too late. And as we have different places in the city, we also have different organs in our body. And using clearing and light chain microscopy, I can visualize the metastasis in the intact organ, and I can see...
No, she didn't.
I will find their favorite spots, and may this be in the crowded pub in the city center or behind some trees in the mountains. I will see them, and I will identify them. And, of course, I also want to do this with metastasis, and interestingly, they seem to do the same. So if we look here, liver metastases seem to barricade themselves, not allowing the T cells to enter, while in the lung, the T cells mingle with the tumor cells, but the tumor cells seem to be undercover. Using different markers, I can identify them, and I can look at the single cell level, and also look at the neighbors, taking the personal details to see what they do. So, I think this is a really nice, equipped with this knowledge, we can actually look into the metastatic environments, and we see and test strategies to capture all our metastases to find them and to improve the treatment for metastatic cancer patients. Any hints are welcome.
All right. So that was great. I just got to say, I love the analogies. I love the way you did that. Personally, And I think it's going to, obviously yield great insights into metastatic processes. Personally, I'm really into translational medicine, and I, think that that's the only shortcoming I see. Is so unless but it's a very nice, very very nice presentation.
Thank you.
No, I agree. You made it fun. I thought it was, fun to look at, to follow. The images are beautiful. I saw them earlier this morning too, in another talk. It's just fantastic job. I mean, making something so beautiful. It's great. Similar question to me, not question, but like intrigue. What's next, or how do you move forward from here? But other than that, it's great. Yeah.
Well, also, I'll say great job. As a father of a 6- and 7-year-old, I loved the whole Where's Waldo kind of start to it, but I kept thinking, where the heck is she going with this? And then you popped up these incredible images. It was really well done. I really loved the presentation. Yes, I'm interested in translation, but I'm a basic scientist by heart. I thought this was great. I thought I had the advantage of being the last one to pick whoever I wanted, but mine's gone. This was great.
What if? What if? Great job. What if? What if I could produce data that was as beautiful as this? Amazing. Honestly, you've absolutely nailed it. Loved it.
Thank you.
I just want to remind the audience that you are judges too, okay? Not just with your spontaneous outbursts of enthusiasm, but on your app, okay?
Teo.
So as we keep going through this, remember who you liked the most from our presenters, because you're going to give the Audience Choice Award. So you're going to be able to vote on your app at the end. But just saying, keep this in mind as we go along. All right.
Vladimir's always a bit keen.
I think our next contestant is Kaiwei Tan. Come on up.
Hi, my name is Kaiwei, and today I will share with you a method to save both time and money in your probe development process.
Amen. I'm listening.
So probe development is a timely and costly process, and all of us know this. But one way that we can accelerate this process is by the use of computational methods and AI. So in our methods, because we also deal with the refinement of our probe, we need to identify methods to streamline this process. And therefore, we use the method known as molecular dynamics. So molecular dynamics uses molecular mechanics of the peptide, the protein, and also the water molecules and ions within the environment to simulate actual binding. In this method, we can identify how each residue is important for binding to the protein of interest, and also how each variation or modification can affect the binding. In our methods, we have shown that, okay, the color is a bit off. In our methods, we have identified, using this method, which modification can affect binding. So in this case, we are calculating the relative free energy change. In this case, if it's positive, there is a reduction in binding, and if it's negative, there's improvement in binding. So as a proof of concept, we then test these in vitro. So we synthesize all of these variants, and we test them in vitro using in vitro granzyme B enzymatic assay. So in this assay, in concordance with in silico, you can see that when it's predicted to be poorer binder, there's also an increase in IC50 around 1,000-fold, indicating that it's a poor binder, likewise in vitro. So you can think of this and extrapolate this. If you were to save the time and money to synthesize that 4 peptides that doesn't bind, that can save your process a lot, and that will be very helpful for labs that there's a challenge in getting fundings and also manpower. So if you're interested, come and talk to me. Thanks.
Whoa. Wait a minute. Where's the imaging? Where's the imaging? We're not in a chemistry conference. I don't know anything about AI. What's going on? Where's the pretty pictures? With poor spatial resolution. Wait! Come on! World molecular imaging. What? Imaging. Yes. World Molecular Imaging Congress. And you put tables in. Where's my lab? I hate tables. I don't understand them. But, you know, save some money.
Yeah.
Now I'm interested. We'll talk later.
Okay.
Yeah, let me just add to that. I think our amazing MC said earlier, I used to play football back in my college days. Let me tell you, I have never heard someone present so much energy about Gibbs free energy calculations. I wanted to run through a wall for that Gibbs free energy calculation. Nice work. I don't really... to add to that, you're going to save 40% of my lab budget? Sign me up.
You could just about afford tips now, right?
Yeah, I mean, sorry, but right now I'm very prone to kind of falling asleep. So I do not like tables. I do not like tables. But other than that, yes, the promise of saving 40%, that's fantastic. That woke me up.
Yeah, so love the energy. Thank you. Kept me engaged. What is? I get we're saving money and that we need to make peptides. What are we using this for? What's the first thing? I didn't get the application exactly as somebody that doesn't use a lot of peptides in my life.
So if you have any targets you're interested in and you want a probe to use it as a PEP imaging probe, MR probe, or whatever, you can use this method.
Okay.
Yeah.
Okay. So I could just decorate my micro bubbles and other things. Okay. I can get behind that. Thank you. Yeah, this is great. All right.
But wait a minute. Who properly uses microbubbles, right?
Oh, we're not going there.
Yeah.
Break it up.
What's the use of them?
All right.
Where's my bubble people?
One lone voice in the back.
I love microbubbles.
I think our next contestant will tell us how to go beyond microbubbles. Let's welcome Dia and Tareel.
I suppose I have to apologize to the judges. It's still not PET.
Wait a minute. Is there
No
some bias
apologies
here?
necessary.
What's going on? 1 second.
So I'm here to talk about biomolecular ultrasound, how to develop pH indicators based on engineered gas vesicles. Engineered gas vesicles. Gas vesicles were really a revolution in the field of biomolecular. They were really the start almost of the biomolecular ultrasound imaging as a field. I see Mikhail smiling in the background. So gas vesicles are small gas-filled protein nanostructures. You may have heard this story already. And they are very similar in a few ways to the invention, to the discovery of GFP for optics. First of all, in the fact that they are genetically encodable, which means we can, for the first time in ultrasound, start looking at the inside of cells, inside cellular environments. But the thing that I'm very much interested in, and I will show you, is that for the first time in ultrasound, we can actually start building sensors. One of the things that GFP did, for instance, one of the first developments from GFP was the development of fluorine, which is a pH-sensitive fluorescent peptide. I show here a graph from Frodo, which is the newest version, what they use to look at phagocytosis, an intracellular process that we can observe. And what makes gas vesicles so suited for being biosensors, something that microbubbles or nanobubbles so far have not been able to do, it's that it consists of two main proteins. So we have a shell protein, GVPA it's called, it makes up this nice cylindrical structure, and we have a reinforcing protein that sits on the outside. It's like a rope pulling it tight. So what happens when we insonify these particles is that these softer particles are way more prone to buckling under the ultrasound pressure, while the stiffer particles remain the same, basically. And that buckling causes a nonlinear behavior, something that we can see in the backscatter, filter out, and we get this super specific behavior. So what my group, or our group, was interested in doing is, can we engineer GVPC and make it sensitive to something, in this case pH. pH is a great biomarker for a lot of things. And we succeeded. The long and short of it is, I can show you that we built a GVPC molecule that reinforces the gas vesicles at low pH and at physiological pH, pH 7, pH 8, weakens them slightly, so we get this nice dynamic range, about 15 dBs. And for the translational scientists, which apparently are in the judge today, we have also done in vivo measurements where we can show. So we can do injections in mice, and we can look at the liver. The liver is filled with macrophages. All gas vesicles are immunogenic. They end up there. These macrophages filter out all the gas vesicles, acidify, and we can actually see that there is a different behavior. So during the first acidification phase, followed by the degradation. So in conclusion, I just want to say we report here the very first pH sensor for ultrasound imaging, and we're very proud of that. So thank you. But yeah, no pet and no pretty images, I'm sorry.
Great. the images are pretty. They're lovely. Yeah, so I loved love the organized presentation, love the innovation. I think there's a big future here. But as as translational effort, I mean, how are we going to take this drifting signal and when do we how are we going to detect pH from that?
So the idea is that we can make parametric maps based on slope. That's the easiest way to go. So if you really do, like these frame rates in ultrasound can be very high. So if you do this experiment for minutes or seconds, you can quite easily take parametric maps of slope and you get these nice images of where you have inflammation, phagocytosis. That's the ultimate goal, to really image inflammation in the context of ischemia or vascular inflammation.
Great. Glad to hear you're thinking about that.
Thank you. The lone person somewhere there.
Yeah, although I do miss seeing an image, that would have been great. But I think you did a great job. You presented it very clearly. I love the idea. I really don't have a pretty big criticism other than, I would like to see this later and when you can actually show some images. But yeah, that's great.
I got to be honest, I was a little on this one. Just a little.
Maybe you're used to the high energy from the last one.
I need Gibbs free energy calculations apparently. I missed this one.
I'm sorry, I don't have those.
Yeah, it's okay. That's all right. No, this just wasn't for me. It sounds like my colleagues to my right are very enthusiastic about this, but it's just it wasn't for me.
Thank you.
I was in a bar yesterday with Mikhail, and we were sharing a drink, and we were just talking about research, and he was telling me, he said, Tim, these microbubbles, they get really, really good papers. Editors love them. They produce beautiful, beautiful images, but secretly, I don't think it's going to catch on.
How dare you? How dare you?
Where's the application? Is this going to happen in humans?
No.
Do we care?
It's not going to happen in humans, not anytime soon. But for test animals, for neuroscientists, this is an amazing tool that you can start looking at, like vascular ischemia in the brain.
But if I was going, one way, what about MR contrast agents that could do just this? Why do you need to go to all the effort to put the gas vesicles in?
As opposed to doing MR?
Yeah.
The resolution, the time scale, we can image faster, we can image at higher resolutions, we can do it live.
Faster, better, cheaper. Where was those MR people? Yes, Dean's over there. Dean, what would you say to that?
That's what I was missing.
It's cheaper, yeah.
It's cheaper. More accessible.
No, you did a beautiful job. It was a great presentation.
Thank you.
All right, I think we have one last contestant, Neisha Martinez-Arango. Come on up.
Ahoy, everyone.
Hi.
All right, so replication of the human immunodeficiency virus can be successfully suppressed with antiretroviral therapy. However, some of these cells are still around, and they can rebound when the therapy is interrupted. These cells are very sneaky, so they hide here in these pockets all over the body called viral reservoirs, and the treatment cannot really reach them and get rid of them. So the cells just, they stay around, very comfortable, until they find a right opportunity to attack again, but not for too long. We believe that with the use of nanobodies, we can actually target these cells. And that's because nanobodies have a very small size compared to antibodies. This characteristic makes nanobodies very attractive. They can go deep into the tissues, they can be cleared faster, they have a very strong affinity with the protein of interest, and you can also label them with short half-life isotopes like F18. So being short has its advantages. So in this case, the nanobody we use is J3, which targets the envelope protein called GP120. Our approach was to use an immunocompromised mouse that we injected with either control or GP120 expressing cells. Once the mice developed the tumors, we injected the F18J3 nanobody, and they underwent PET-CT imaging. Images speak more than words, right? So in this top image, we see how there is fast clearance, low background, and we see a specific uptake in the GP120 tumor here in bright green, something that we don't see in the contralateral control tumor. We also confirmed these results ex vivo when we dissected the tumors and we stained for GP120 protein, which expression we see here in red, and as expected, we don't see it in the wild-type cells. So here we have it, our new Avenger member, J3, the promising nanobody that aims to target HIV-latent cells with the power of molecular imaging. Thank you.
We're ending on a high with some pet images. Whoa, come on, let's go! Come on. I love how you just sneaked in the word sneaky. This is brilliant. You just have to sneak that in every time. Yeah, look, I love it. What I love less is text on a slide. So first thing that I hate is a table, second text. All right? You can, again, ask my lab. I really hate it very much. But you've got a sleeping cell, right? So, you know, it totally makes up for it. So congratulations. The data's beautiful. I love it.
Thank you.
Yeah, I actually could not agree more. I thought that well, I guess we'll start with my only critique was I thought the text was too much. It detracted from how amazing I thought this presentation actually was. I know I lost my card already, but I would still love to buy you a drink later if you're up for it, to talk to you more about this. I think this is really cool. Great job.
Yeah, I can't agree more with everybody. I think you're going to get, same thing here. Beautiful images. I love you made it fun. I love your cartoons. But I'm trying to read, and I actually have pretty good vision, but I was having a very hard time trying to get the labels here. And so, yeah, just no text. Yeah.
Who said that? Who said that? Scott, get up here. Get up here, Scott. You're off the committee. Oh, no, I have no say in the committee next year.
I don't have anything to add after all this. How can I even think around these people? No, it's lovely. It's lovely. And actually, I also generally don't like text, but being outside of this particular area and having not seen some of the things that you're doing here, it helped me. Although I did have to kind of stare at it. I wasn't able to, look at you and get your communication. But that would be the only thing. So it's wonderful.
Thank you.
All right. All right, let's give all of our contestants a huge round of applause. All right, now comes a crucial moment, all right? The judges are going to turn off these microphones and deliberate among themselves. Okay, maybe we'll just take away these microphones from you for about, 3 to 5 minutes. During that time, all of you are judges too. So pull out your app, the WMIC app, find the Science Slam lunch session under Saturday, open it, and go to evaluations. Okay, and then within that, you can vote for your first place, second place, and third place favorites, all right? So for the next couple minutes, just sit there, enjoy, and vote, and we'll get back together in 2 or 3 minutes.
So we're just going on the scores. We don't want to maybe deliberate about if there's anything. Yeah. Because I thought there was. Well, why don't we? Yeah. Well, maybe we go to the back again. Yeah. Let's do that. Well, guys, great job. Sorry. You're a big boy.
Everyone, feel free to sing along. I know Andre Martins will want to sing this. All right, while the judges are completing their deliberations, I want to announce what the prizes will be. Okay? So if you are simply the best, then your prize will be $500. If you are simply the second best, then your prize will be $200. If you're simply the third best, then it's going to be $150. And if you're the audience favorite, then everybody here will remember you forever. Give you high fives anytime they see you here or at Prague Airport tomorrow morning or anywhere around the world. All right? So those are the stakes. Judges, are you ready? You seem pretty opinionated when you were up here. We had to have an arm wrestle, which I won. Okay. All right, come on. All right, does anybody have a molecular imaging joke? Did you hear the one about radio imaging? Radionuclide imaging? I heard it's a modality that's in decay. I knew that joke would resonate with certain MRI people. I think Charles probably has an ultrasound joke.
I do, but you can't hear it. Wow. Y'all really are pet people.
All right, come on. All right, are you guys ready? All right. Judges, announce your verdicts.
Well, I think Narissa's going to come to stage to announce the awardees.
All right.
Yeah.
Okay, so I'm the first. I'm just going to announce the audience favorite first, and that goes to Gina Dunkel. Jean,
come up.
Come on stage. Simply the best. All right, so it has been very hard to arrive to this conclusion because I'm that Asian who doesn't know math a lot. But anyway, I were able to get into, so this is hard for me and for the judges to decide, but our third placer is Neisha Martinez. Come up here. I can imagine myself as Oprah, like, you win, you win, you win, right? But anyway, the second place is Gina Dunkel. All right, for our first place, drum roll please. All right, the first place goes to Victoria Laney. Sorry, Tim, it's not Pat.
Can I just say, though, wow, what an amazing selection of presentations. It was fun playing the bad guy. Of course, I was in character, right? But
why are you always in character?
It's just nice to be in character from time to time. No, but thank you so much, guys, for the amazing work. I was thinking back to my time when I was a grad student and a postdoc, and there's no way I would have been able to produce the quality that you guys have done. So let's thank them once again. That's amazing.
And a big round of whatever reaction you're feeling for our four judges. No, but I think they deserve a big round of applause for. Thank you very much.
Can we also give a hand to our Master of Ceremonies, Mikhail Shapiro?
We love you, Mikhail. All right, thanks.
All right, you can clear out.